Okay.
You from the state in China?
Welcome back. Before I get started on the next lecture, any question about what we discussed this morning? Something you want to come back to or elaborate? No? Okay. So this lecture is now we move a little bit outside of the frame of the map I used to guide you a bit through these different topics. So moving a bit towards more advanced question. That's the first lecture treating something a bit different than the pure hardcore numerical optimal control. Even though we'll go back to these questions from this point of view. So what we have done so far is called direct optimal control. I'll try to explain the distinction here. And there's another family of approach to optimal control problems, which is called indirect. And I want to cover that a little bit. I'm just wondering how many of you know about this indirect approaches? Yeah, one? Not so many. Okay, so it's good to have this discussion. I mean, spoiler alert, at the end of the day, it's not different. But the way of thinking about the problem is different. The equations you solve are different until you go all the way down to what you redo in the computer, and then you see that things reconnect. But I want to show you a little bit what people do in that context. Okay, so it's based on the Pontryagin maximum principle, Pnp. You heard about this? Yeah, a little bit. Okay. And so we'll discuss that and see a little bit how actually you can do numerics on these equations, and also solve problems, the similar problems that we do in direct optimal controls, with a few drawbacks, which is one reason why direct approaches are a bit more successful than these ones. Okay, so before diving in, I think it would be good to backtrack a tiny bit about optimal control approaches. And we always discuss something like this, an optimal control problem. Here so I have stage cost, or like some people call it the Lagrange cost and terminal cost, some dynamics, and some initial conditions. You may have inequality constraints on top of that. And I would argue that you can divide the different methods you can apply on solving these problems into these 4 different families. And so what we discussed so far is really only this family here. So there's quite a lot to discuss behind that. And there's pretty much as much to discuss behind all of them. I will not do that, but every one of these guys have quite a lot of stuff behind. Yeah, and I divided the different families. So I don't know if you recognize these different things. Some, a bit, yeah. So yeah, I'm going to discuss a bit this family here today. And then you have these families that I will not touch in this course, but they're also quite interesting. And I think it's useful to classify them in this table in order to get some orientation and what happens in the end. So the methods we discuss here, they are local methods, which means that you converge to local solutions. You cannot prove that you have found a global solution to your problem. That's what I mean by local. Global methods would deliver the global solution. So when you have solve the equations, you know that there's nothing better you can do to your system. It does not depend on initial guess and so on. The price to pay is that typically these methods are awfully expensive to use in practice. On that column, you're actually writing continuous equations describing optimality, so typically differential equations. And on that side of the table, you write discrete equations. So all we've done with direct optimal control, was based on discretizing the dynamics. So we write discrete equations. So in this family, we end up with the KKT conditions. That's your discrete equations describing optimality. And same with dynamic programming. You also write discrete equations. So PMP, Pontryagin maximum principle, is 4 simple problems based on doing that. So you write a so-called Hamiltonian function. I'll label it H. You have also the notion of multipliers, the lambda, and they actually do play the same role in the approach, though people often call them co-states in indirect methods, but it's kind of the same thing, and it's actually in some context giving you even the same numerically the same object. So L is the cost you have in your integral, and then you form this scalar product between these multipliers and the dynamics and the OD you may have. And now it's the solution to optimizing this problem, finding the U that minimizes this cost function, is given by minimizing this function H over U. So you receive a state and a co-state, and you find the minimum of that function over U, and that's going to be the optimal input. Of course, so that will be for a given state, and you need to know the co-states. And what's going to happen is that these states and co-states, they are defined by differential equations. The one for the states is quite obvious. That's your model. So x dot equals f of xu. That's really your dynamics, essentially, with imposed initial conditions. And the co-states, the dynamics of the co-states, is given by the gradient with respect to the states of this h function. And you have terminal conditions to respect on the co-states. That's the gradient with respect to the state of your terminal cost that you need to evaluate on the final state of the problem. Does it make a bit of sense, these equations for you? You can identify the different objects in here. So we'll discuss a bit more how you approach them, of course. But that's the basic stuff you have behind solving optimal control problems using the PMP approach. So essentially, you can already guess, we'll discuss more of that, but guess a little bit what happens here. You could imagine if I was to give you the lambda at t0 at the initial time of the problem. If I was giving you that, you could basically integrate this dynamics. So x dot is given by fxu, lambda dot would be given by this thing here, and you could at any time instant find u by getting the minimum of this function over u. So you could write an integrator that receives x and lambda as states in the integrator, so basically lumping the states and co-states, and integrate this forward by computing at every time instant the u as a function of x lambda. You can almost see this guy as a feedback on the state co-states that comes into your equations. And the feedback depends on x, and you need to process this guy at the same time in order to compute the inputs. Okay? Problem is we don't have lambda at time 0. We don't know what it should be. So in that sense, one thing that happened on the way is we did not discretize the input at all. So in all these direct approaches, the first step, regardless of what we do, is to describe the input profile in a finite dimensional space. For example, piecewise constant, or some piecewise polynomials, or something like this. One way or another in direct approaches, you would discretize u. Here you don't necessarily discretize it. I mean, the computer in the end you will, but in the equations you don't. You could define a u at any time instant as a function of x lambda. So in that sense, u in the equations remains an infinite dimensional object, if you want. It's a function of time. I'll mention that in the end. I will omit state constraints in the problems because they are very hard to handle in this context. It's possible, but it's not easy. Okay with that? So if we just go back quickly to direct optimal control, in comparison to that, we'll always start with discretizing the problem, typically discretizing at least the inputs, sometimes the states as well. And then we write an NLP instead of the optimal control problem. So there's a very, very striking difference in what we do in that sense. So we replace the input by a finite dimensional object instead of an infinite dimensional one. And what we gain typically, and that's the reason mostly why direct approaches are used more in practice than indirect, because you can treat any constraints you want pretty much in that context. There are some applications where indirect methods are justified to use over direct ones, but they are like very, very specific. Okay, so in that sense, people would often argue in the community that the very big first distinction you have between different families of methods in optimal control, you may have heard these terms before, first optimize, then discretize, and the converse, first discretize, then optimize. And in that sense, it's a bit misleading maybe, but what people mean by that is in these families, you will first write down the continuous equations that describe your solution. For example, the Pnp, you write differential equations for the states and co-states and define your u as the minimization of h. So in that sense, you first write equations describing optimality. Then when you want to solve it, usually you need to discretize them and solve that in the computer. So you end up there anyway, but you first write down conditions of optimality and then discretize these conditions. As opposed to direct optimal control and also dynamic programming, if you apply DP on continuous problems, you would first discretize the dynamics and then write equations that describe optimality. For example, the KGT conditions. Okay, so you can actually find that in the literature and in some papers and discussions around optimal control and this kind of terms. Okay, but let's dive in a bit further with this Pnp principle. So again, now we start from a continuous optimal control problem. Very simple one, so stage cost, terminal cost, some dynamics, initial conditions, and let's ignore the rest for now. So you start with writing your Hamiltonian function. So it's a scalar, huh? So L is scalar and lambda transpose F will be scalar as well. You would get your control from minimizing this function with respect to u. Spoiler alert, in many problems, it boils down to solving this equation, right? You want the gradient of h to be 0 with respect to u, right? Which we often write this way. And then you basically have to process these equations. So you can imagine here I'm building a simple example with a single state and that matches a single co-state. The lambdas would always have the dimension of the states, huh? So that you can form this scalar product. And here I would basically integrate my dynamics from 0 to the final time 2. And if I pick some lambda at t0, I can basically integrate these equations. At every time instant, my u is given by this equation, and I could process this dynamics. And in this example, I have a trajectory for the state, a trajectory for the co-state. So that's my initial condition for the state. It's given here. And in principle, I should satisfy also something at final time. My lambda at TF at the end of the integration, it should match the gradient of the terminal cost evaluated at my final state, so at that point here, right? So I have something that should match at the end, and it's not really obvious how I should build my problem so that I respect this condition. You see that? Is it obvious or not really? Not? Maybe if you tell me what is, or if you put me on the right track for helping a bit.
Where I'm not?
Yeah, or if you ask some questions, yeah.
Why should lambda be equal that term?
Why do we have this condition?
Yes.
Right, okay. That's a tricky question. Actually, why do we have that condition as well? I will not discuss that. We would have to go into variational analysis. That will be another lecture. Yeah, another time I could discuss that. But it's coming from principles of optimality. So this is a set of conditions you need to respect. Or let's put it differently. If you satisfy these conditions, they are necessary such that there is no other use in the neighborhood that are better in some sense. It will be coming from saying, if that's my u of t, these conditions imply that it's not possible to find another u in the neighborhood that performs better. There may be another one somewhere really out there that performs better. That's why it's a local solution, but not locally. Yeah. Okay, so let's go back to this. So if I have my initial conditions for x and lambda, I would be able to process this dynamics. Is that okay for everyone? Yeah. The problem is that no one is giving me this lambda t0. So I don't know how to process this dynamics. I don't know how I could integrate this ODE forward, even with my u given, because I don't know where I should start with lambda. So we call that a two-point boundary value problem, TPBVP. It's common to see this abbreviation in this context. And here is the problem. So you could try to integrate these equations forward. So just start from x t0, lambda t0, integrate until tf, and hope that this condition would hold somehow. But you don't know what lambda t0 you should use, so you cannot really do that. You could imagine if I have the initial condition here and like somehow I have the terminal condition here, I could in principle integrate x forward to final time, then use this to get lambda tf, and then I could come back here backward in time and build the trajectory lambda, so doing like a forward backward integration. The problem is we don't know u if we don't have lambda. So I cannot, in principle, generate this state trajectory without knowing lambda at the same time, because I need my lambda to find my u, right? So I cannot do something like forward and then backward either. Okay with that? An interesting feature is that actually if we could find lambda t0, that's a vector, right? That's it has the size of the state, and that's my initial condition for lambda. If I knew my lambda t0, then I have basically solved the problem. If I know the correct lambda t0 such that when I integrate these equations starting from x t0 and lambda t0, at the end I satisfy this equation, then the problem is solved. So in some sense, the degrees of freedom I have in solving my problems are just of the size of lambda t0. And the unknown variables I should solve my problem over, they are actually of the size of the state only, as opposed to, for example, lots of like a rich parameterization of the input profile. Okay with that? Okay, well, we've seen tools to handle this kind of problem. Essentially, in some sense, I have equations that I need to solve, and I don't know how to solve them explicitly, but we have a tool for solving equations. That's Newton, essentially. So I could, in principle, basically, I know my xt0, and I could guess my lambda t0, right? Could guess that. If I have this, I can process my trajectories forward in time, right? Could integrate the differential equations here. And then I could check if at final time, the final TF I get is matching the conditions I'm having on its final value, right? Oops. So I could check if that holds. I could guess lambda t0, integrate everything, and check this final condition. And I mean, obviously, if I guess lambda t0 randomly, there's little chance that this is gonna work. But then I can apply Newton on that condition. So I could use Newton on that condition. And here the variables that I will manipulate are the lambda t0. So I could basically differentiate that condition with respect to lambda t0. And we've seen how to process the sensitivities inside integrations and so on and so forth. So you could do that and then take Newton steps on this. So doing something like changes in the lambdas given by this thing here. So essentially Newton steps on these conditions and steps on lambda t0. Does that make sense? So the algorithm will look like this. So you have x0, you guess lambda at t0, I'll note them x0, lambda 0. So you have this one, you guess this one, that's the variable you will try to optimize or solve for. You generate the trajectories and then using these equations, and then you basically compute how this conditions is satisfied. So do I have this equals to 0? And you would evaluate the sensitivities of this condition with respect to lambda 0. That's about sensitivities of simulations. And then you would do a Newton step. And you go back again until this condition is satisfied, right? And then your Newton steps will adjust the lambda zeros until the terminal condition is satisfied. So that's how you can solve a TP-BVP. Okay with that? Okay, let's make an example, a simple problem. Still nonlinear, non-convex. So I have just a quadratic cost function here. So that's my L, 1/2 x squared plus u squared. I have some nonlinear dynamics, scalar, and just to make it simple, x dot equal u minus sine x, some assigned initial condition. I'm going to try to solve this problem using this principle. And we can now look a bit how things work. So can dissipate some mysteries. So my Hamiltonian function, I need to do L, that's this guy up here, plus lambda times f. F is simply this function here. and lambda is scalar, size of x. So I have lambda times u minus sine x. Now if I have to find u, I'm talking about minimizing h with respect to u. So I can do del h del u, which in this case is u and plus lambda. Right, I'm just differentiating that with respect to u. And I want this to be 0 because I want to find the minimum, which implies that u is minus lambda, right? So if I know lambda, I know u. And then I can form a simple two-state differential equation, x dot equals my f, where u is replaced by minus lambda. So I have an equation in x. And my equation in lambda, that's actually easy. I do need to do del h del x. So in that case, I get x minus lambda cos x, I guess. Yeah. And my lambda dot is minus that. So lambda cos minus x, that looks good, yeah. And I don't have any u appearing in here. So now I have a differential equation in x lambda. I could integrate that if I have my x 0 and lambda 0, right? And then the terminal condition, if you remember, lambda tf, well, actually it's written here. Lambda tf should match the gradient of the terminal cost at tf, but I don't have any terminal cost in here, so my phi is 0 essentially, which means that my lambda tf, it's 4 here. I chose 4 for the terminal time. So lambda at 4 should be 0, right? And then we could deploy this. So integrate for a given guessed lambda 0 and apply Newton steps on this. So here is an example. Let's put this guess. Lambda 0 is 0.36. And then I will show you where I start and what Newton is doing with this. And you see here, my x0 is 1, it's given. I start my lambda at 0.36. U is given by this at every time instant. And if I integrate these things forward and plot the u at the same time, I see this happening, okay? And here my lambda final at time 4 is not 0, so I don't have the solution, actually minus 4 something. Now I'll use Newton to adjust that, and Newton will basically manipulate lambda 0 in order to bring lambda 4 at 0. And you see here it's pretty good. Right, a few Newton steps, and we have adjusted lambda times 0 in order to hit the targets lambda 4, 0. Now you see a nice optimal solution. So you apply some u that drives this x towards 0 in a decent time, and that minimizes this problem. Okay? So this type of approach works. You can apply it. You can even solve very challenging problems with that. Any question on this? Okay. Now, obviously, the story does not stop here. Here I chose lambda 0 is equals 0.36. Okay, that's one choice. Not really telling you why I chose that. And actually, Newton will move this lambda 0 to 0.466. Okay, so that's the lambda more or less that should be used. Let's try a different guess now. Let's try to move this lambda 0 somewhere else. And actually, I'll pick a guess that is closer to the final one. So I move from 0.36 to 46. Let's start with 0.41, for example. Why not? Kind of hopefully helping by coming closer to the correct lambda. So we do the same story. Newton tries to adjust to get lambda 4, 0. And here is what's happening. It's like going a bit into space right now. Lambda 4 is 38, decreasing. Okay, Okay, better. Oh, it's increasing again, and it's basically going all over the place. Okay, so not easy. I picked a slightly different guess, and it does not converge at all. This problem is very well known for indirect methods, and it has very, very good explanations. First thing we can do on this specific problem, we can try to understand how lambda 0 relates to lambda at any time in the simulation. And in some sense you have seen that picture before when we discussed the nonlinearity of propagating dynamics. Here on that axis I have my lambda 0, and on that axis I have my lambda after a while or a bit of integration. So here I integrate for 0.4 seconds or time units, and that's the lambda I get out of these equations. So for a short time, the relationship lambda 0 to lambda at 0.4 is fairly linear. Actually, there's really no problem with that. So it should be easy to adjust lambda 0 to get lambda 4 equals 0. You can almost see that on the graph. But as we saw before, actually, if you start integrating for a longer time, the picture at some points changes drastically. So 1.6, we're still good, but we need to hit the target at 4 seconds. 2 seconds, not bad. 2.4, okay. And then things start twisting around. And at 4, you actually have a fairly nonlinear function. Looks like this in this case. So for example, if you linearize around here, Newton will think that you need to go all the way there to solve the problem. Actually, all the way there to solve the problem. But that's really not what should happen, actually. Okay with that? There is a very nice mathematical explanation of what's happening. It's a bit more abstract. I think it's nice to know it or see that once in your career. Okay, if you imagine for a second, it's easier to see that in a very small problem like the one we discussed. So you can imagine your initial conditions, x0, lambda z. Yeah.
So in the previous question, where in the previous slide, where you have shown the nonlinear relationship between lambda 0 and lambda t.
Yeah.
So do we have any basis through which we can guess the value of lambda 0?
No, that's a problem. We have no idea what it should be.
So if we don't guess it properly, then we will be interested.
Yeah. I'll show you later how you can solve this problem. Actually, it's not very hard to solve, but you need to approach it in a very good way. Actually, you already know the solution, but you will see that. Okay, so imagine that for a second. So you can imagine something in 3D now. I put x0 and lambda 0 here, and then I put time here. And you can think if you start your simulation at a specific x0 lambda 0, that's going to be a point in that plane here. And when you simulate forward, you have a trajectory that will move forward in time, right? See that? Okay. If I start somewhere else, I will have another trajectory, and so on and so forth. Now what's interesting, you could imagine what happens if I consider like a volume of initial conditions. You imagine you take all these points and you simulate all these points forward, and you wonder what's going to happen to this volume as it's simulated forward. You see that concept? Right. And what will actually, it's not very complex what's going to happen, but the question is what will happen to the volume. In that case, it's basically the surface of this thing. How will it change in time? So like this thing here, for example, how many x meters or x squared you have in some sense. Like what is the surface of this one at time 0? And what's the surface of this one at some time t? So that's what I'm trying to do here. You consider a domain in this x lambda space, this D. It would have some boundary, this thing here. So that's D, and that's your boundary of D. And we wonder how this surface D will evolve in time as you process the integration. And so the volume of this D, labeled it rho, it's basically the integration over that volume of elements of surface. This kind of notation can work. And if you don't understand that, it does not matter so much, but you can write how this volume changes in time, and it's kind of strongly connected to physics. If you want to know that, the best is to understand how how the flow is happening inside your boundary. So you have del D, and you're wondering the flows of x dot lambda dots, how they are traveling through this boundary to make it larger or smaller. So in that sense, we integrate over the boundary the x dot lambda dots by the normals to this surface. If you remember your courses in physics, this is the thing we use in magnetic, for example. So that's this, and then classic trick in physics, when you have something like this, you can apply the Green theorem, and you go back to an integration over the volume of the divergence of this flow x dot lambda dot. So don't worry if it's a bit abstract. The bottom line is that this guy here will be 0. That's coming from the way the equations work for x dot lambda dot. You can take that offline if you want. And what happens in the end is that this term is 0. When you integrate it, still 0. So del over dt of this rho is 0. In more simple terms, if you take a volume of initial conditions and you simulate them forward, this volume will not change. You keep the same volume. This is much deeper than Pontryagin maximum principle. You find these things all over the place in quantum physics, actually. Anyway, back to the example. Maybe it's easier if we actually see what happens here. So here is your x and lambda space at the initial conditions. Here I draw a small circle in here, and I'm gonna simulate this circle forward, see what happens to it. So here is your time and the initial conditions. If I simulate this circle forward, what happens to it is this. So it's the surface this thing has is not changing, but it becomes awfully distorted. Okay, where I'm going with this, it's actually fairly simple in the end. Since the volume is not changing, and if one of your states or your co-states are stable, so going to 0, then the other one has to go to infinity. If you think about it, if along x all your initial conditions in time are going towards 0, for example, because they are stable, then a volume will basically collapse along something very thin. So the co-states will have to diverge, essentially. It's coming directly from the conservation of volume. To put it more simply, either one of these guys is unstable. Either the dynamics of x are unstable, or the dynamics of the co-states are unstable. They cannot be stable both at the same time. And if you remember a little bit from what we discussed with shooting methods, handling unstable systems in simulations and numerics, it's a bit complicated. Okay with that? A simple consequence, and the TP-BVPs are very hard to solve numerically. So what can we do with that? You know the answer already. You can do multiple shooting. So you can divide the problem of solving this divide this TBBVP problem into smaller problems that you will connect together via constraints. And actually, when we teach multiple shooting, we usually explain that in the context of direct optimal control. But multiple shooting as a principle has been invented first for indirect methods, and then it was applied or extended to direct methods. So the very original papers about multiple shooting, that was for indirect methods. Okay, so you can think of the problem that way. I'll just group my states and call states into, let's call it S, for example. Can think of this as a big dynamic in X and lambda. U is given as a function of S. It's always minimizing the Hamiltonian. So when you know X lambda, at least we assume that you can know U from this, for example, like we did in the example. And then you have dynamics for S. So S dot is given by F for the X and this gradient of H for the lambdas. And what we will do is basically discretize this dynamics on a time grid. So instead of trying to simulate my S, so the X lambda, all the way to the end and try to adjust or meet some target at the end, I will basically decompose that into smaller intervals and disconnect them. So I'll end up with solving something like this. My S's will evolve on this discrete time grid. And I can reconnect everything via constraints. And that would look like this if this zeta here, I guess it's xi, if that's an integrator for my dynamics over some time intervals. So if I give my x S0, that's my psi of S0 and S1 integration and so on and so forth. I can write something that looks very much like our shooting gap constraint. So initial conditions imposed for x0, and then the end of the integration of my state co-states at the end of the first interval should match the initial conditions for the second, and so on and so forth, all the way to the end. And then I can add my terminal conditions, which is lambda at final time should meet the gradient of the terminal cost. Okay, it's always easier to look at things in an example. So we go back to this guy. And so essentially what I'm going to do is integrate these guys over shorter time interval. And when we try to do this, like solve the problem in one shot, integrate everything to the end, and then adjust these conditions on lambda, we are doing single shooting. So we do everything at once, and you have this problem that you iterate and it goes nowhere. Now you could divide things. Here I do 3 intervals. So that's my states co-states at the beginning. Then I introduce a new state co-state initial conditions in some sense here, and a third one here. And then I'll integrate things and try to close the gaps again, like we did in direct methods, and also satisfy the terminal conditions on lambda x at the end. So 3 intervals. It's still a bit tricky, doesn't really go anywhere. Okay, let's make it 5 intervals, and then it works very nicely. Few iterations, you converge, and so on and so forth. More intervals, it helps converging faster, right? So that's the trick again, multiple shooting for this method. Okay, we take a break, and then we discuss a few more things.